Deep inside the Earth is a solid metal ball that spins independently of our rotating planet, like a top whirling inside a bigger top, shrouded in mystery. This inner core has intrigued researchers since its discovery by Danish seismologist Inge Lerman in 1936. How it moves, its rotation speed and direction, has been at the center of a decades-long debate. Evidence suggests the core's spin has changed dramatically in recent years, yet scientists remain divided over what exactly is happening and what it means. The challenge lies in the fact that Earth's deep interior is impossible to observe or sample directly. Seismologists have gleaned information by examining how waves from large earthquakes behave as they pass through this area. Variations between waves of similar strengths that traveled through the core at different times enabled scientists to measure changes in its position and calculate its spin. Differential rotation of the inner core was proposed in the 1970s and 80s, but it wasn't until the 90s that seismological evidence was published, said Dr. Lauren Wasik, a senior lecturer of physical sciences at James Cook University in Australia. Researchers have debated these findings due to the challenge of making detailed observations of the inner core, owing to its remoteness and limited data. This has led to disagreements on the rate of rotation and its direction with respect to the mantle. Some analyses even proposed that the core didn't rotate at all. A promising model proposed in 2023 described an inner core that had spun faster than Earth itself in the past but was now spinning slower. For a while, the core's rotation matched Earth's spin. Then it slowed even more until it was moving backward relative to the fluid layers around it. At the time, experts cautioned that more data was needed to support this hypothesis. Now, another team of scientists has delivered compelling new evidence. Research published June 12 in the journal Nature not only confirms the core slowdown but also supports the 2023 proposal that this deceleration is part of a decades-long pattern of slowing down and speeding up. The new findings confirm that the changes in rotational speed follow a 70-year cycle, said study co-author Dr. John Vidal, Dean's Professor of Earth Sciences at the University of Southern California. "We've been arguing about this for 20 years, and I think this nails it," Vidal said. "I think we've ended the debate on whether the inner core moves and what its pattern has been for the last couple of decades. Not everyone is convinced that the matter is settled. How a slowdown of the inner core might affect our planet remains an open question, though some experts say Earth's magnetic field could come into play. The inner core, buried about 3,220 miles deep, is surrounded by a liquid metal outer core. It is made mostly of iron and nickel and is estimated to be as hot as the Sun's surface. Earth's magnetic field yanks at this solid ball of hot metal, making it spin. At the same time, the gravity and flow of the fluid outer core and mantle drag at the core. Over decades, the push and pull of these forces cause variations in the core's rotational speed," Vidal said. "The sloshing of metal-rich fluid in the outer core generates electrical currents that power Earth's magnetic field, protecting the planet from deadly solar radiation. While the inner core's direct influence on the magnetic field is unknown, a slower spinning core could potentially affect it and also fractionally shorten the length of a day." When scientists attempt to see through the planet, they track two types of seismic waves: pressure waves, or P waves, and shear waves, or S waves. P waves move through all types of matter, S waves only move through solids or extremely viscous liquids. Seismologists noted in the 1880s that S waves generated by earthquakes didn't pass all the way through Earth, concluding the core was molten. However, some P waves, after passing through Earth's core, emerged in unexpected places, creating anomalies that were impossible to explain. Lerman first suggested these wayward P waves might be interacting with a solid inner core within the liquid outer core, based on data from a massive earthquake in New Zealand in 1929. By tracking seismic waves from earthquakes that have passed through the Earth's inner core along similar paths since 1964, the authors of the 2023 study found that the spin followed a 70-year cycle. By the 1970s, the inner core was spinning faster than the planet. It slowed around 2008, and from 2008 to 2023 began moving slightly in reverse. For the new study, Vidal and his co-authors observed seismic waves produced by earthquakes in the same locations at different times. They found 121 examples of such earthquakes between 1991 and 2023 in the South Sandwich Islands. They also looked at core-penetrating shock waves from Soviet nuclear tests conducted between 1971 and 1974. When the core turns, Vidal said, it affects the arrival time of the wave. Comparing the timing of seismic signals as they touched the core revealed changes in core rotation over time, confirming the 70-year rotation cycle. According to the researchers' calculations, the core is just about ready to start speeding up again. Using only pair earthquakes reduces the amount of usable data, making the method more challenging. However, it also enabled scientists to measure changes in the core rotation with greater precision, Vidal said. If his team's model is correct, core rotation will start speeding up again in about 5 to 10 years. The seismographs also revealed that during its 70-year cycle, the core's spin slows and accelerates at different rates. This suggests the inner core might not be as solid as expected. If it deforms as it rotates, that could affect the symmetry of its rotational speed, Vidal said. The core's different rotation rates for forward and backward motion add an interesting contribution to the discourse. Yet, the depth and inaccessibility of the inner core mean uncertainties remain. As for whether the debate about core rotation has truly ended, more data and improved interdisciplinary tools are needed. Changes in core spin are all but imperceptible to people on Earth's surface. When the core spins more slowly, the mantle speeds up, making Earth rotate faster, and shortening the length of a day by mere thousandths of a second. Scientists study the inner core to learn how Earth's deep interior formed and how activity connects across all subsurface layers. The boundary where the liquid outer core envelops the solid inner core is especially interesting, filled with potential for activity. Because the spinning inner core affects movement in the outer core, it helps power Earth's magnetic field, though more research is required to understand its precise role. The mysterious region, where the liquid and solid meet, is still filled with questions. There is much to be learned about the inner core's overall structure.